Hi, in this video we'll be looking at Unit 3, which deals with chemical reactions. Now in our chemistry course we are 13 weeks into the course, so let's go ahead and get started. So for our agenda we'll be looking at balancing equations, and we'll be looking at multiple types of balancing equations, including combustion reactions, double displacement reactions, single displacement reactions, synthesis reaction, and decomposition reactions. So our lesson objective is very straightforward. Students will learn how to balance a chemical equation. So let's go ahead and get started. Balancing chemical equations. According to Dalton's law, in a chemical reaction, whatever you start with, you're going to end with, because matter cannot be created nor destroyed. So if you start with 100 atoms, you have to finish with 100 atoms. They might be rearranged, and we refer to the rearranging of molecules as a chemical reaction. But whatever you start with, that's what you're going to end with. So a good analogy would be this picture right here at the bottom. In this picture, what you see is a motorcycle on the left and also a motorcycle on the right. Both are motorcycles. Now they've been rearranged. The motorcycle on the left is one whole piece versus the motorcycle on the right is in pieces. But nevertheless, they still are balanced because they have the same amount that you started with as you finish with. Now, some terms that you should know as we balance equations. On the left side of the arrow, those are referred to as the reactants. So CH4 and O2, those will be our reactants. On the right side of the arrow, you refer to that as the product. So where you have the CO2 and the H2O. The arrow, though, is referred to as actually the yield. So there's the left side of the yield and the right side of the yield. The large number in front of the molecules here is known as a coefficient, and the small number here is known as the subscripts. In balancing a chemical reaction, you never change the subscripts. Never. Those remain the same. It is the coefficient that are added or taken away in order to balance a reaction so that you end with the same amount of molecules that you started with as you ended. So now we're going to go ahead and take a look at 3 different examples. For our first example, it's going to be 4 different chemical equations. This is a very simple double or single displacement reaction, and then we have other very simple reactions. For our example number 2, we'll be looking more at combustion reactions, so we're increasing the difficulty level a little bit more. And example 3, this will be the more challenging problems where we're dealing with double replacement reactions, and these will require a little bit of extra work to go ahead and work them out. So we're going to go ahead and start with example 1. So let's go ahead and start with example number 1. In example 1 you have A, B, C, D. Here's letter A. We have chlorine reacting with potassium bromide, and that will yield potassium chloride plus Br, which is bromine. So we're going to start by counting how many atoms we have on the left side of the reactant side and how many atoms we have on the right side, which is the product side. So we're going to begin with chlorine. There's a small 2 right there. That means we got 2 chlorines. K, there's no number. No number means that there's a 1. Maybe I could add it there for a little bit extra help. And Br, there's only 1 of those. So there you go. That's how many atoms I have on the left-hand side. On the right-hand side, which is a product K, there's only 1 of them. Cl, 1 as well. And Br, there's 2. Alright, so our goal is to get all of these numbers to match up. So we begin by thinking, alright, which one can we work with? Let's just start from top to bottom. Chlorine. Chlorine will be an easy one to start with. Alright, so you always look at the small number and ask yourself the following question. What could I multiply this number, a 1, so it can match that number? Again, you always look at the small number and ask that question. So you can say, well, I could multiply chlorine by 2. Alright, so if I multiply chlorine by 2, so let's see. That means I'm going to put a 2 here, and I'm going to distribute like it would in math to the potassium and to the chlorine. So it'll be 2 times 1, 2, so now we got 2 potassiums. And now we'll have 2 chlorines, because 2 times 1 is 2. Alright, so I've got the chlorines to match, now they are balanced. So we continue going down and asking the same question again. Now let's look at the potassium. The potassium, okay, what number could I multiply this 1 so it can match that 2? Again, you look at the smaller number and ask that question. What could I multiply the 1 so it can match a 2? So the answer for that would be, I need to multiply potassium by 2. So I'm going to do that. So here's the potassium. On the left hand side, that's the reactant. So multiply it by 2. 2 times 1 will give me a 2. And a 2 times 1 will give you a 2 as well. And notice now all of them match. So now we have a balanced reaction. The blank represents really a 1. If we did nothing, then we'll multiply times 1. So our answer is for every 1 chlorine, there's 2 potassium bromides, and that will yield 2 potassium chlorides and 1 bromine. Alright, so that will be a balanced equation for letter A in example 1. Up next is letter B. For this one, we have nitrogen gas reacts with hydrogen gas to give us ammonia, which is a molecule that has many uses. And again, we're going to go ahead and start by counting how many atoms we have on the reactant side and how many we have on the product side. So we have 2 nitrogens and 2 hydrogens. On the product side, we got 1 nitrogen and we got 3 hydrogens. So again, I'm going to go ahead and start at the top. Nitrogen is not balanced. We have 2 on the left, 1 on the right. So the question again, you look at the smaller of the 2, the 1 in this scenario, and multiply it by, what number can I multiply this one so it can match our bigger number? So multiply it by 2. So if I multiply 1 times 2 is 2. So the nitrogen on the right, I want to multiply it by 2. So put the coefficient right there. And it distributes to both the N and the H, changing. So it will be 2 times 1. That becomes 2 nitrogens. 2 times 3, that becomes a 6. Alright, so we got the nitrogens matched up. Up next for us, we're going to go ahead and work with the hydrogen. So again, you look at the smaller numbers on the left. So this is referring to that hydrogen. And you ask yourself, what can we multiply this number so you can match that? So we're going to multiply by 3. So 3 times 2 will give me a 6. So I'm going to put a 3 here. 3 times 2. That will go ahead and give me a 6. And now they match up. Alright, so again, any blanks represent a 1. So for every 1 nitrogen, we need 3 hydrogens, and I'll give it 2 molecules of ammonia. So that is problem A and B. Next, let's go ahead and take a look at letter C from example number 1. And here we have sodium reacts with oxygen gas to go ahead and give us sodium peroxide. So let's go ahead and solve this one. We're going to go ahead and count how many atoms we have of each. So we're going to begin sodium. There's only 1 of them on the left hand side. That's the reactant side, and 2 oxygens. So I write it down. Over on the product side, we got 2 sodiums and 2 oxygens. Alright, so for this problem, the oxygens already matched. So we really only have to concern ourselves with sodium. So what I'm going to go ahead and do is, I'm going to look at sodium, and you look at the smaller number, and you ask yourself, what could I multiply this 1 so it equals a 2? The answer would be, if I multiply 1 times 2, that will give me 2. I should multiply the sodium by 2. So I'm going to do that, put a 2 right here, 2 times 1. That gives me a 2, and now everything matches. The leftovers, those blanks, remember they represent 1. So for every 2 sodiums, there's 1 oxygen gas. That will yield 1 molecule of sodium peroxide. For letter D, we're going to go ahead and do the same, where we're going to go ahead and begin by counting how many atoms of each we have. Again, when there's no number, that represents that there's a 1 on the subscript. So there's 1 carbon and 8 sulfurs. Over on the product side, we have 1 carbon and 2 sulfurs. Alright, since the calcium is already balanced, we're not going to work with that. Let's go ahead and work with the sulfurs. So what number can I multiply 2 so that it equals 8? And the answer for that is 4. If I multiply 4 times 2, that will equal 8. So I'm going to go ahead and do that. So for the S, which is on the right side, I'm going to multiply it by 4. Sometimes students put the 4 in between. No, it goes in the front. The coefficient always goes in the front, and it distributes to both atoms. So it'll be 4 times 1 is 4. 4 times 2 is 8. Now notice how previously I had the carbons balanced. They're no longer balanced. And that's okay. That happens sometimes while dealing with attempting to balance a different atom. In this case, I did manage to balance the sulfur, but the carbon's no longer balanced. But that's okay. Then we go back and fix it. So now, again, we have a 1 and a 4. And you ask yourself, what number can I multiply the 1 so that equals 4? So say 1 times 4 equals 4. So I should multiply it times 4. So that's the carbon. So look for the carbon. I'm going to go ahead and put a 4 here. 4 times 1, that gives me a 4. And now both of these are done. Everything matches. So for every 4 molecules of carbon that reacts with a one molecule of sulfur, now it's going to go ahead and give us 4 molecules of carbon disulfide. That takes care of example 1. In example 2, we'll be looking at combustion reactions. And combustion reactions, you see them right here, they all have the same reactants and the same products, where you have a hydrocarbon at the beginning. Now the subscripts do change for it, and it reacts with an oxygen, and it produces carbon dioxide and water. So let's go ahead and get started with letter A, and then we'll take care of letter B. So at first you always count how many atoms you have on the left hand side and how many atoms you have on the right hand side. So let's begin. For carbon atoms, there are 5 on the left, 12 hydrogens, 2 oxygens. For the right hand side, carbons, we only have 1 here, 2 oxygens, 2 hydrogens, and another oxygen. Now instead of writing 3, I'm going to go ahead and put 2 plus 1. Why? Because, well, the oxygen here is separate from this oxygen, so maybe I'll put a coefficient that will only affect this oxygen and not that one, so it's easier for me to actually leave them separate that way. Alright, so let's go ahead and get to work on these. For our first one, let's go ahead and work on the carbon. The carbon has a 5 on the left, 1 on the right. So always the question that you ask yourself is, for the smaller number, you look at it and say, what number can I multiply the small number so you can match the bigger number? So the answer for this one is I'm going to multiply 1 times 5, and that will give me a 5. So that means I'm going to multiply carbon by 5. So I put it here, 5, and I distribute to the carbon and to the oxygen. So it's going to give me a 5 here, and this oxygen refers to that one right here, so it's going to be 5 times 2. So then now this 2 now becomes a 10. Alright, so we've got our carbons to be balanced. Next, let's move along to the hydrogens. Same question, what number can we multiply this 2 so you can match that 12? The answer is if I multiply 2 times 6, that's going to go ahead and give me a 12. So for the hydrogens, I'm going to multiply it by 6. I'm going to put a 6 right there. It distributes to the hydrogen and to the oxygen. So 6 times 2, that is a 12. So I'm going to put a 12 in its spot. And 6 times 1, that's this oxygen, 1. 6 times 1 is 6. Alright, so now we got our hydrogens. They are matching, 12 and 12. Now for our oxygens, we got 16 oxygens on the right hand side, on the product side. We need 16 oxygens on the left hand side. So again, you look at the smaller number and ask yourself, what could I multiply the small number so you can match the bigger number? What could I multiply? What number times 2 gives me 16? The answer for that is 8. 8 times 2 will give me 16. So for the oxygen on the left, I want to multiply it by 8. So I'm going to put a 2 here. I'm going to put an 8 in front of the oxygen and multiply 8 times 2, and that will go give me 16. And that is our balance equation for letter A. Moving along for letter B, it's going to be very similar since it's another hydrocarbon problem. We have 3 carbons and 8 hydrogens, 2 oxygens. Over on this side, it's going to be 1 carbon, 2 hydrogens, 2 oxygens, plus 1 more oxygen from there. Again, they're in separate molecules, so I put them separate. I go ahead and I begin by taking care of the carbons. For the carbons, I want to go ahead and get them to match. So what number times 1 gives me 3? The answer is 3. 3 times 1 is 3. So I'm going to multiply a carbon on the right times 3. So I'm going to put it right here. Now that distributes to the C and the O. So 3 times 1 is 3. And that 2 refers to that second oxygen, so 3 times 2 is 6. So I'm going to replace that 2 with a 6. Next, let's go ahead and work on the hydrogens. And for the hydrogens, I want to go ahead and make them match again. So what number times 2 gives me an 8? The answer is 4. 4 times 2 gives me an 8. So I'm going to put a 4 in front of the hydrogen. So 4 times 2, that's this one. I'm going to replace it with an 8. Now they match. And 4 times 1, right here, that's this one. So we'll have a 4. So we got the carbons and the hydrogens, and now those are balanced. But up next, let's go ahead and deal with the oxygen. We have 10 on the right, only 2 on the left. So same question as always. What number can I multiply this to so it can match the 10? So the answer is 5. 5 times 2 gives me 10. So I'm going to put a 5 on the left hand side. It's 5 times 2, multiply. That will give me a 10. And that will go ahead and balance the equation. Now, of course, any blanks here or there, that means 1. So for this one, for every 5 pentane molecules, you need 8 oxygen molecules. That will give you a yield of 5 carbon dioxides and 6 water molecules. For letter B, for every 1 propane molecule that combusts with 5 molecules of oxygen, that will produce a yield of 3 carbon dioxide molecules and 4 water molecules as well. Up next are problems C and D. And for problem C, they give us this molecule, which is cyclobutene, and they asked us to go ahead and solve for it, balance reaction for its combustion. And for nonane, we also got to go ahead and figure out the balance reaction for its combustion. So we begin by counting how many atoms we have of each element on the left side, which is the reactant side, and on the right side, which is the product side. So we got 4 carbons here, 8 hydrogens, and 2 oxygens. Over on this side we have 1 carbon, we got 2 oxygens, 2 hydrogens, and 1 more oxygen, who again I'd like to put them separate because they are in 2 separate molecules. Alright, so let's go ahead and now begin with balancing the carbon. So that's going to be first. So to get the 1 to match a 4, so I'm going to multiply 1 times 4, that will give me a 4. So I'm going to multiply the carbon by 4. That distributes to the carbon and the oxygen, so 4 times 1 gives me 4. 4 times 2, that's this 2 oxygens, that's going to go ahead and give me an 8. Next, let's work on the hydrogens. For the hydrogen, here we have a 2 and an 8. So what can we multiply 2 so that it can match an 8? So multiply the 2 times 4, that's going to go ahead and give me an 8. So I'm going to multiply the hydrogen by 4. So that's going to be 4 over here for the hydrogen, because 4 times 2, that gives me 8. So now you have 8 hydrogens, which makes a match. And you distribute to both the hydrogen and the oxygen. So 4 times 1 is just 4. Last step for us, let's go ahead and balance the oxygen. On the right hand side we got 12 oxygens total, so we want 12 on the left. So what number can we multiply 2 so that it could be 12? The answer is 6. 6 times 2 gives me 12. So I'm going to put a 6 in front of the oxygen. 6 times 2 gives me a 12. And now everything matches. Again, for any blank spots, it's really a 1. So for every 1 cyclobutane, that gives me, you'd require 6 molecules of oxygen gas, and that will yield 4 molecules of carbon dioxide gas, plus 4 molecules of H2O, water. Let's go ahead and move along to letter D now. We have 9 carbon molecules and 20 hydrogens and 2 oxygens on the reactant side. On the product side, we got 1 carbon, 2 oxygens, 2 hydrogens, and plus 1 more oxygen from here. 2 from here, 1 from there. There they are. Alright, so let's go ahead and begin with carbon. Carbon, again, what number can we multiply times 1 so that it equals 9? That's an easy answer, 9 times 1. So we're going to multiply carbons by 9. Distribute to the carbon and the oxygen. 9 times 1 is 9, so now they match. Oxygens, 9 times 2, that goes ahead and gives us 18. So those are not matching yet, we'll deal with that in a second. Let's go ahead and wrap up now the hydrogens. We have 20 on the left, 2 on the right. What number can we multiply by 2 so that it equals 20? The answer is 10. 10 times 2 gives me 20. So I'm going to multiply the hydrogens by 10. 10 times 2 gives me a 20. And 10 times 1 gives me a 10. Alright, so that goes ahead and takes care of the carbon and the hydrogen. Now for the oxygens, we got 28 oxygens on the right hand side. So what number can multiply by 2? That will give me 28. So the answer is, if you multiply by 14 oxygen, that will go ahead and give us 14 times 2, 28. And now all of these match. So for every 1 molecule of nonane, you need 14 molecules of oxygen to react with, and that will yield 9 molecules of carbon dioxide plus 10 molecules of water. Alright, that takes care of example number 2. Up next is example 3, and in this type of problems we'll be looking at double replacement reactions, which you can see right here. They're a little bit longer and therefore a little bit more difficult than it is the combustion reactions or the single replacement reactions, synthesis or decomposition reactions. So Our double replacement reactions, here's letter A and letter B. We have sodium hydroxide reacting with hydrogen carbonate to give you sodium carbonate and water molecules. So we're going to do much of the same, where we count how many atoms we have on the left side as we do on the right. So on the left side, which is the reactant side, sodium, there's only one sodium. Oxygen, you'll notice it in two places. Here's one of them, there's three, so I'm going to put 1 plus 3. I keep them separate because they are in two separate molecules. It makes my life a little bit easier. Hydrogen, there's one hydrogen here and two there, and again I'm going to keep them separate since they're separated by the positive sign right there. And finally carbon, there's only one carbon, so there we go, counting everything on the left. For everything on the right, I'm going to go ahead and count them. There's 2 sodiums, 1 carbon, 3 oxygens here, 2 hydrogens there, and 1 more oxygen here. Now, while choosing which molecule should I begin with, normally I just go ahead and start at the top, and I might end up doing this, but let me go ahead and tell you one that I do not want to start with. Either the oxygen or the hydrogen, I do not want to start with either one of those. Save them for last, because notice they are very much complicated molecules. There's atoms for oxygen in pretty much every single one of these, so we're going to save that one actually for last. You want to start with something easy. And for our first one, carbon's already balanced. We're not going to start there. We're going to start with the sodium. You have a 1 and a 2. So then you ask yourself, what number can I multiply the 1 so it can match the 2? So the answer is multiply 2. 2 times 1 is 2. So you always want to get the small number to match the bigger number. So I'm going to put an 2 in front of the Na. So here we go. And don't forget that that distributes to the Na, the O, and the H. So I'm going to put my arrows there. And so there's going to be 2 sodiums. Now 1 oxygen. This 1 oxygen is this one right here. So I'm going to switch that to a 2. 1 hydrogen is this one right here. So I'm going to switch that one to a 2 because 1 times 1, 2 times 1 is 2. So there you have it. Next one, again, we're going to go ahead and look the C. Well, that's already balanced. We're not going to touch it. Alright, so let's go to the next easiest one. The next easiest one will be the hydrogens. It's easier than the oxygen, so I just want to keep it as simple as possible. Alright, so I'm going to go ahead and look at the hydrogens. On the left hand side we have 4, on the right hand side we got 2. So again, you always look at the smaller one and ask yourself, what can I multiply this by so it can match the bigger number? So multiply the 2 times 2, that'll give me a 4. So I'm going to put in front of the hydrogen a 2, and that distributes to the hydrogen and to the oxygen. So that is going to go ahead and turn into a 4, because 2 times 2 is 4. And this 1 is this 1 oxygen is this one right here. So 2 times 1 is 2. So I'm going to erase it, put a 2 in its place. And if you actually take a moment to look at that, now every single molecule is balanced. Even the oxygen, which we didn't even work with, is already balanced. Here you have 5, there you have 5. And the carbon, we never had to do anything with it, it stays the same. For our blank spots, we're just going to go ahead and put 1 and 1. So that's our answer. For every 2 sodium hydroxides, you need 1 hydrogen carbonate, and that will yield 1 molecule of sodium carbonate and 2 molecules of water. Let's go ahead and take a look at now example B. In example B, we get this molecule, H3PO4 hydrogen phosphate, and it's going to react with potassium hydroxide, and that's going to yield potassium phosphate and water molecule as well. So again, we count how many of each atom we have. We have 3 hydrogens there and 1 hydrogen there, so I'm going to put 3 plus 1, 3 here and 1 there. P, there's only 1 phosphorus. There's 2 oxygens, 4 here and 1 here, so I'm going to put 4 plus 1. And potassium, there's only 1 of them, and everything's accounted for. Now on the other side, let's see, we got 3 potassiums, so I'm going to put that here, 1 phosphorus, 4 oxygens, 2 hydrogens, and 1 oxygen as well. Alright, so those are our starting numbers. Again, what I'm looking for is something easy. I don't want to start with hydrogen, that's a 4 and a 2. The oxygen, much too difficult, actually they're already 5 and 5. P is 1 and 1, so we're going to start with the potassiums here. So here's a 1, that's a 3, you look at the small number and you say, what number can I multiply this number so it can match that number? So multiply by 3, so I'm going to put a 3 in front of the potassium. Now that 3 distributes to the K, the O, and the H. So that's going to be 3 times 1, that gives me 3 for the potassium. The oxygen, this 1 oxygen here is this one, so it's going to be 3 times 1 is 3. and the oxygen refers to this one right here. So I'm going to erase it, and 3 times 1 is 3. Alright, so we got the potassiums all done. Next, the phosphorus, they're also all done, so we don't have to do anything to them. So what we're going to work with next is now the hydrogen. For the hydrogen, we have 6 here, 2 there. And I chose the hydrogen over the oxygen because it's got less digits, so therefore it's a little bit easier. So what number can multiply the 2 so it can match the 6 on the left? So we can multiply the 2 by 3. So I'm going to multiply hydrogen by 3. Put it over here. 3 times 2, that gives me a 6. And 3 times 1, that gives me a 3. Alright, so that balances everything out. Again, any blank spots means 1. So for every 1 of the hydrogen phosphate, you need to react with 3 potassium hydroxides, and that will yield 1 potassium phosphate plus 3 water molecules. That takes care of example 3, part A and B. Up next for us is part C and D of example number 3. So let's go ahead and take a look at both of these double replacement reactions. For our first reaction, we have barium chloride reacting with hydrogen phosphate, and that will yield barium phosphate plus hydrogen chloride. So let's go ahead and take a look at counting. How many of each do we have so far? So BA, we have 1. Cl, we got 2. H, there's 3 of them. P, 1. And O, there's 4. That's for the left side, which is the reactant side. I put them on the left side. On the right side, I'm going to go ahead and put these guys right here. There's 3 BAs. Now, how many phosphors are there? There's 1, since there's a number. But notice how it's in parentheses, and there's a 2 outside. So you distribute that number as well. So in reality, there's 2 phosphorus and 8 oxygens. And for hydrogen chlorine, there's only 1 of each. Alright, so let's go ahead and solve this problem. I'm going to go ahead and start at the top. BA, there's 1 on the left, 3 on the right. So I'm going to go ahead and multiply this number times 3, because 3 times 1 will give me 3. So for the BA, I'm going to go ahead and put a 3 right here. Alright, that's going to distribute to the BA and the Cl. BA, that's going to be 3 times 1, that's 3. So I'm going to erase it, put a 3 in its spot. And for the Cl, which is right here, is 3 times 2, that'll give me a 6. So there you have it. Up next, let's go ahead and keep on working with the Cl. That's up next. So we're going to go ahead and multiply. What number times 1 will give me 6? The answer for that one will be 6. So I'll multiply for the Cl, which is right here. So I'll put a 6 right here in the front. And the multiply times the H and the Cl. So it's going to give me a 6 here and a 6 there as well. Alright, up next for us is going to go ahead and be the hydrogens. For the hydrogens, we have a 3 here and a 6 right there. So what number can multiply the 3 so it can match the 6? And the answer is we're going to multiply it by 2. So I'm going to put a 2 in front of the hydrogen. So here we have it. I'm going to put a 2. 2 times 3, that gives me a 6. I also multiply it times the phosphorus and the oxygen. So 2 times 1 is 2. And 2 times 4, that's 8. Alright, so there we go. Every single number is balanced. So 1 right here. If it's blank, put a 1. So for a balanced reaction, for every 3 barium chlorides, you need to react it with 2 hydrogen phosphates that will yield 1 molecule of barium phosphate and 6 molecules of hydrogen chloride. Alright, now letter D. For letter D, we're going to go ahead and again start by counting how many of each atoms we've got. So we're going to start with aluminum. There's no number here, so it's a 1. Nitrogen, there's no number there, so it's a 1, but it's inside parentheses and a 3 outside, so you distribute it. So it's going to be 3 times 1, 3 nitrogens, and 3 times 3, 9 oxygens. There's another oxygen here. Sodium, there's only 1. That oxygen is accounted for, and 1 hydrogen here. Alright, so that is what's on the reactant side of the yield. On the product side, which is on the right hand side, let's see, there's 1 aluminum. Oxygen, again, there's 1, but you multiply times 3. Hydrogen, there's 1 times 3 is 3 hydrogens. 1 sodium here, 1 nitrogen here, and 3 more oxygens right there. So now that we've got all of those, let's go ahead and solve. For the first one, I'll start with aluminum, and notice that aluminum's already balanced 1 and 1, so there's nothing to do there. Nitrogen's up next, 3 and 1. So I'm going to multiply the right side where the nitrogen's at by 3. And that's going to match that 3 right there. So look for the nitrogen. Here it is. I don't put it in between the Na and the N. It's got to go in the front. So I put a 3. And you distribute to every single atom here. So it's going to be 3 for the sodium, 3 for the nitrogen, and 3 times 3, that's 9. That's, this oxygen is 3 oxygens. This one multiplied by 3, now that's a 9. Alright, 4 ups. Next, oxygen. I don't want to deal with it. It looks a little bit too challenging. Let's leave it for later. Sodium. Sodium's up next. That's a 1, that's a 3. So if we multiply 1 times 3 is 3. So sodium, that's a 3 here. 3 times 1, that's going to give me a 3 here. Distributed also to the oxygen. That's this oxygen right here is this one. So 3 times 1, that gives me a 3. And finally, 3 times 1 is 3. Now notice every single number, it's balanced out. The blanks are 1s. Let's put a 1 here and a 1 right there. So for every 1 molecule of aluminum nitrate, you're going to require 3 molecules of sodium hydroxide. And that will yield as a product 1 molecule of aluminum hydroxide plus 3 molecules of sodium nitrate. So those are the balance equations for letter C and D. And that brings us to the end of the lesson for week 13 of chemistry. Thank you so much for watching.